Welcome to our first online lecture. I hope you guys are as excited as I am to jump in and get started. We are starting a brand new unit today. Yay! Unit 3, Exponential Models. So before you clicked play on this lecture, hopefully you guys completed page 90, the workbook launch for 3.1. It's called Cell Growth. It's on page 90 of our workbook, and I hope that you took 15 to 20 minutes to complete that, to complete our launch. And if you haven't done that, I ask that you please stop this lecture right now, open up your workbook to page 90, and complete that launch before you start this lecture. We are working with the Algebra with Models student workbook that we've been working with in class since the beginning of the semester. I have the 2018 edition. This is by Marion, Anton, and Karen Santoro. Okay, so again, if you have not completed the launch on your own first, please stop right now, open up your workbook, complete the launch, and then join us again and click play when you're done with it. Okay, so let's get started. Okay, so before we jump into exponential functions, let's just quickly review what a linear function is, because you're going to see that there are certain components of linear functions that we can compare to components of exponential functions. So a linear function, right, a linear relationship, we can describe using the equation y equals mx plus b. And we talk about functions a lot in this class, so we can also call it we can also describe it using f of x equals mx plus b, where m is our constant, right? It represents the slope or the constant rate of change of our line. And we know that to calculate m, we divide the change in output by the change in input. So this is hopefully a review for you guys, right? The change in our y's over the change in our x's, that gives us our rate of change. We also know that in our equation, b is a constant, which represents the y-intercept, or the initial value. X represents our independent variable, or our input, and y, or f of x, represents our dependent variable, or our output. Okay, so bottom line, we can describe a linear relationship using the equation, or using the function f of x equals mx plus b. M is our slope, our rate of change. B is our y-intercept, or our initial value. X is our input, y, or f of x, is our output. Okay, these are important things, and we're going to sort of see how we can write an exponential function in a similar fashion with a little bit of a twist. Okay, so let's start our lunch. Hopefully you're opened up to page 90. Hopefully you've filled in your answers to the questions. The first thing we are going to do is just think about this situation, you guys. One of the most important things you can do for yourself is, while you're at home online learning, is to really make sure you take the time to think about the questions that I'm asking you. Just like when we were in class and I would ask you a question, you would raise your hand to answer. We don't have that benefit now, so you need to work that much harder to make sure that you are taking the time to stop and think about these questions as we go through. So in class, whenever we have a launch or a new situation, I always tell you to just stop before you answer any of the questions and visualize what's happening. Make a movie in your head. Really think about and see in your mind what is occurring with whatever situation you're given. So here's our situation. A scientist spent 30 days researching new bacteria. What a coincidence with everything going on right now. After every day, each cell splits into 2 cells as pictured below. And I grabbed this picture directly from your workbook, okay? So let's think about what's happening here. On day 0, right? 0 days have gone by. We have this cell, okay? We have 1. And every day that passes from here on out, the cells are going to split into 2 pieces, okay? So I'm starting with 1 cell. Now, a day has gone by, and that cell has split into 2 pieces, right? So on day 1, I now have 2 cells, right? 1 day has gone by, and I have 2 cells. That first cell, it split into 2 pieces. Okay, so now let's see what happens after 2 days have gone by. Okay, so I had 2 cells, and now each of those cells is going to split into 2 pieces. So the first cell is going to split into 2 pieces, and the second cell is going to split into 2 pieces, which leaves me with 4 cells, right? The first one splits into 2. The second one splits into 2. I have 4. Now 3 days have gone by. I had 4 cells, and each of those 4 cells is going to split into 2 pieces. Split, 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 right? So now I have 8 cells. Now 4 days have gone by. On day 3, I had 8 cells. Now each of those 8 cells is going to split, 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 split into 2 pieces, which leaves me with, and I'm going to disappear for a second so you guys can see this, 16 cells. Okay, so every day, every time another day goes by, these cells, however many we have, are each splitting into 2 pieces. Okay, I want you to stop and think about that for a second. And throughout this slideshow lecture, you're going to see me write these words, stop and think, with the little stop symbol and the little think symbol. And that is your cue to pause this lecture and really think about or work out what I am asking you or what is happening. So right now, I literally want you to just stop for like a minute, pause this lecture, and think about what's happening. Visualize these cells splitting into 2 pieces every single day, and visualize the kind of growth that's going to come from that. And you can already start to see it in the picture. So guys, press pause and stop and think about what is happening in this situation. Okay, so hopefully you guys have visualized what's occurring in this situation with these cells just growing and splitting and splitting and splitting and splitting every day into 2 pieces. And you have some sort of a picture in your head of what's occurring and some sort of idea of what's happening. The first question that your workbook asks you, letter A, says, without doing any calculations, write an estimate for the number of cells after 30 days. Just guess. Be brave. You guys, I am not expecting the correct answer right now. I am literally just asking you to be brave and take a guess as to how many cells you think there will be after 30 days have gone by. So remember, every day, each of those cells is splitting into 2 pieces. And then each of those is splitting into 2 pieces. And then each of those is splitting into 2 pieces. So this has been going on for 30 days. How many cells do you think there are? Stop and think. Hit pause. Write down a number. Look at your number that you already wrote down. Okay, just stop and think for a second. Do you think it's 40 cells? You think it's 1,000 cells? You think it's 1,568,232 cells? Whatever you think, you should have a number on there. And guys, there is no wrong answer. This is your opportunity to be brave. Use what you just thought about on the previous slide with what's happening and make an educated guess. Okay? It doesn't have to be the right answer. This class is about exploring. Okay? Take 1 minute to think, write your guess in your workbook, look at whatever you guessed before, okay? Get some sort of an idea in your head. Okay, so now we can move into letter B, identify and label the variables including units. Guys, I always say labeling your independent and dependent variable is like the key to unlocking the problem. So if you take time to be really thoughtful here, the rest of this problem will sort of fall into place for you. And labeling our variables, that is something we've been working on since day 1, but it is something that continues to give us difficulty. So we really, really want to take that time to be thoughtful about it and to make sure that we're thinking about it. So our 2 variables here are, right, number of cells and the number of days that have gone by since we had our very first little cell there that split. Okay, so we're thinking about number of cells, number of days gone by. which is our independent variable, our input, and which is our dependent variable, our output. So I want you to take a moment, hit pause, stop and think about what you think would be our independent variable and what would be our dependent variable. Okay, so now that you've hopefully thought about it for a moment, let's think about it together. So which sentence makes more sense to you? The number of bacteria cells depends on the amount of days gone by, or the number of days gone by depends on the number of bacteria cells. So we're thinking about, we want to know how many bacteria cells do we have, right? Well, that depends on the amount of days gone by. The number of bacteria cells depends on the amount of days that have gone by, right? Our bacteria cells are just going to keep splitting into two pieces every single day. So every time another day goes by, each of our bacteria cells is splitting into two pieces. So if the number of bacteria cells depends on the amount of days gone by, that means our dependent variable is the number of bacteria cells, which I am calling C, and my units are number of cells. Don't forget your units, guys. Don't do it. Don't be silly. Remember to put it in there. Which means that our independent variable, our input, is the amount of days gone by, which I am giving the smart variable D. And my units would, of course, be the number of days. Okay, you guys, so now we can move into letter C. Make a table of values, then examine the table for a pattern. Is it linear? Why or why not? So this is really just asking us, does this have a constant rate of change? This goes back directly to what we did in Unit 2 when we talked about linear functions. We would look at our table of values, and we'd look at our inputs and our outputs, and we'd see if there was a constant increase or a constant decrease. That was our slope, right? Our rate of change. We would look for our rate of change. As our inputs were constantly increasing, or our outputs either constantly increasing or decreasing, right? That's what we did in Unit 2 to try and define our linear functions. And if we could find that constant rate of change, then it was indeed a linear function. Well, this question is asking us to do the same thing. It's asking us to make a table of values, look at what's happening from one input to the next and what's happening from one output to the next, and determining if there is that constant rate of change. So the first thing we have to do is make a table. And we're going to do that using our input, our independent variable that we just defined in letter B, the slide above, and using our dependent variable, our output that we just defined. So I have my table here. On the left side, I've put my inputs, my independent variable, which we said was the number of days gone by, and we called that D. And on my right, I have my output, the number of cells, which we called C. So here I have it as C of D. Okay. Always your input goes on the left and your output goes on the right every time you make one of these tables. So before we start looking for that rate of change, let's just talk about where I even got these values from. Where did my inputs and my outputs come from? Let's talk about that first. So remember, we visualized what was happening. We have our cells, and each day they're splitting into two pieces. So on day 0, right? No days have gone by. 0 days have gone by. I started with that one cell. And what happened to that one cell? It split. So after 1 day, that cell split into 2 pieces. So now I have 2 cells. Okay. Well, now another day is going to go by. And each of those 2 cells is going to split into 2 pieces. So after 2 days, I'm going to have 4 cells. Right? Makes sense? Those 2 cells I had, they each split into 2 pieces. So now I have 4 of them. Okay, well now another day is going to go by. So now it's 3 days later. And each of those 4 cells has split into 2 pieces. So now I have 8 cells. And this is going to keep happening, right? 4 days, after 4 days have gone by, I'll have 16 cells. After 5 days have gone by, I'll have 32 cells. After 6 days have gone by, I'll have 64 cells. After a week, I'll have 128 cells. And after 8 days, I'll have 256 cells. Okay? So every day, we have cells each of our cells is splitting into two pieces. So now that we have our inputs and our outputs, we have this table of values. And you can go as many days as you want into it. But I stopped after 8. I thought this was enough data for me to really try and determine a pattern. Right? You want to make sure you have at least a handful of data points in there to work with. Right? Don't just do 1, don't just do 2. Do a few so you can really examine it for a solid pattern. Now I can look to see if there is indeed a pattern there. So I'm going to shrink myself so that we can look at this. All right, let's start with our input. Okay, and let's see what's happening. So from 0 days have gone by to 1 day having gone by. Well, that's an increase of just 1 day, right? From day 1 to day 2, that's an increase of 1 day. To go from 1 to 2, we add 1. To go from day 2 to day 3, we're adding 1. Day 3 to day 4, we're adding 1. And as it turns out, we're just adding a day along our inputs. So our inputs are indeed increasing at a constant rate. Great, that's what we would want. So now let's look at our output, our number of cells. Remember, we're thinking, is this linear? So when we are looking at our outputs, we also would be very happy if we saw a constant increase or decrease. And we know that this is increasing, so we're looking for a constant increase. So let's check it out. Right, we know our input is increasing by a constant of +1. Okay, that's important. All right, let's look at our output. Well, we started with 1 cell, and after a day we had 2. So to go from 1 to 2, we added 1. So far, so good. All right, well now we have 2 cells, and the next day we had 4. To go from 2 to 4, what do? I add 2, right? 2 plus 2 gives me 4. Now I've increased by 2. So first I increased by 1, now I increased by 2. Well, let's keep going. Let's go a little bit further. This is getting fun, getting a little curious, right? So now I had 2 cells, or excuse me, I had 4 cells, and then I went to 8 cells. The next day I had 8. So to go from 4 to 8, what do, you guys? I added 4. Oh my goodness. So first I added 1, then I added 2, then I added 4. Whew. Okay. I'm already thinking, I don't think this is increasing at a constant rate, but let's just do another one for fun. All right, so now I have 8 cells, because this is getting pretty interesting. And I increased to 16. How do I go from 8 to 16? Well, I added 8. Oh my goodness. So really, I'm now sure that this is not increasing by a constant rate. And in fact, if we kept going, we would then add 16, and then 32, and then 64, and then 128. Holy guacamole, what is happening here? So I know, I can see the output is not changing by a constant. First, it increased by 1, then 2, then 4, then 8. These numbers are indeed getting bigger, but they're not the same. Constant means the same, right? I am not just increasing by 1 every single time. I am increasing by 1, then 2, then 4, then 8, then 16. So my output is not changing by a constant, which means this is not a linear function. This does not satisfy what it needs to be a linear function. I would need a constant rate of change. I don't have one here. So, oh my goodness, what the what? What exactly is this crazy function? What's going on? We have this constant increase on the left, my input, but on the right, my output, it's increasing, but by more and more and more and more and more each time. What is this? And so I want you guys to stop. Okay, so hopefully you've taken some time to sort of stop and think about what was happening with this crazy function that really threw us for a loop on the last slide. We know it's not a line. We saw that, we figured it out. So what on earth is this? So let's move into letter D. It says, after examining the pattern of this function, can you figure out how to write an equation for it? All right, so we really sort of need to look at this table of values again and reevaluate it, now knowing that it is not linear. This is not increasing or decreasing at a constant rate as we define a line. Okay, we were okay with the inputs, right? We felt comfortable with that. We saw we were just adding 1 because we were just going up from 1 day to the next, right? 1 to 2, 2 to 3, 3 to 4. So on the left side of our table, our inputs, we were just adding a day every time. We felt comfortable with that. It was the right side of our table, the output, that sort of really threw us for a loop. That was like wild and crazy, these cells, right? Every day, the amount of cells was increasing by a different amount, which was like, whoa, what is happening here? So we couldn't define this as a line. It just didn't work, right? Our change from one output to the next, it was not constant. We weren't constantly adding the same thing. We saw that we were constantly increasing, so we are getting bigger, but it's not by adding the same thing over and over and over again. So we don't have that constant rate of change that we would see for a line. So let's see if we can sort of find another pattern, maybe a different pattern that would suit this particular data table here, this particular set of data. So we know that we can't add the same thing from one output to the next. Let's see if we can figure out a different way to get there. So I make myself small so we can sort of talk about this. So we're going to really focus on the output for this. So on day 0, no days have gone by, right? We had one cell. Well, and what happened to that one cell? It split into 2 pieces. So first we thought, well, to go from 1 to 2, I just add 1, right? But as we came to find out, that didn't work as we went down our table. We weren't just adding 1 every single time. So I need to sort of think about maybe there's a different way I can go from 1 to 2. Is there another operation or another way that I can get from 1 to 2? Think about that for a second. Well, yeah, you guys, there is. I can multiply by 2. 1 times 2 equals 2, right? So to go from 1 cell to 2 cells, I can multiply by 2. Interesting, isn't it? This is getting kind of interesting now, kind of exciting. Let's explore this. Let's see if it continues to work. So then the next day, I went from 2 cells to 4 cells. Let's see if this new pattern holds. So to go from 2 to 4, will it work if I multiply by 2? Yeah, it does. 2 times 2 is indeed 4. So again, here I multiplied by 2. Ooh, now I'm getting excited. Now I'm getting excited because I may just have stumbled upon a pattern here. Okay, well, let's explore some more because we're good mathematicians and we know we need to really see if this pattern holds, okay? So we need to keep exploring a little bit more with it. So then I went from 4 cells to 8 cells. Okay, let's see if that holds with our pattern. Can I multiply by 2? Well, think, what's 4 times 2? Ha 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 ha! It's an 8! It does indeed hold. So again, I multiplied by 2. And as it turns out, you guys, if we kept going with this, it holds for every single value. Every time I jump from one output to the next, I am indeed multiplying by 2. So, isn't this so interesting, you guys? We have this new function where we are increasing, but it's not because we're adding. We're increasing because we're multiplying. So we aren't increasing because we're adding a constant. We're increasing because we're multiplying by a constant. How interesting is that? So I'd like you to take a moment to just stop and think about that. So hopefully you've taken a moment to stop and think about this crazy new function, right? We have these cells splitting, these bacterial cells splitting into 2 pieces every day. Each cell splits into 2, and it's growing and it's growing and it's growing. And we just figured out this awesome new realization that while we're increasing, we're not increasing by adding a constant. We're increasing because we're multiplying by a constant. And this is the key to our exponential functions that we're learning about and exploring today, you guys. And as it turns out, that constant has a name. So like when we were doing linear functions, we called it the rate of change. When we're doing exponential functions, it's going to be called the constant multiplier. So in this function, we have a constant multiplier of 2. And Exponential tables are characterized by constant multipliers of the output when the input increases by a constant. So with lines, we had the input always increasing by a constant and the output increasing by a constant or decreasing by a constant. Well, now we have exponential functions and an exponential table of values, which we have the inputs increasing by a constant, but the outputs are being increased by a constant multiplier. Super cool, right? So we have our brand new exciting function here. We've just stumbled on an exponential function. All right, so now let's talk about how do we calculate constant multiplier? What is it? What do we do? And in order to figure that out, I just took a little subset of our table. So I just took a piece of the table. I didn't take all 8 days. I just went from I went from 1 day gone by to 4 days gone by. And we're going to actually look about what we're doing with the constant multiplier to go from what output to the next, okay? So if I am at day 1, right? 1 day, excuse me, I should say, if 1 day has gone by, I had my 2 cells, and I know, because we figured it out in the slide above, that I'm multiplying by my constant multiplier of 2 to then get to 4 cells. So that means after 2 days now, I know I've gone from 2 cells to 4 cells. All right, well, what about my next output? After 3 days have gone by, how many cells will I have? Well, I know that I'm going to take my 4 and I'm going to multiply it by my constant multiplier of 2, and that gives me 8 cells. So after 3 days have gone by, I have 8 cells. And again, how do I know how many cells I'm going to have on day 4? Well, I take my 8 cells, I multiply it by my constant multiplier of 2, which gives me 16 cells. So after 4 days have gone by, I now have 16 bacteria cells, right? This is what our constant multiplier is doing. We are starting at one output, and to get to the next one, we're multiplying by 2. We're multiplying by our constant multiplier. So we take our current output, we multiply it by our constant multiplier to get our next output. That is how our constant multiplier functions. That's what it's doing here, okay? We are going from our current output times our constant multiplier of 2 to get our next output, right? If our current output is 4, we multiply it by 2, we get our next output of 8. If our current output is 8, we multiply by 2 to get to 16, right? That's what we're doing here. So just like when we were doing linear functions and we were trying to figure out what's our rate of change, right? What is our slope? What is our m? We had a formula that we used. We did y2 minus y1 over x2 minus x1. We did the difference of output over the difference in input. That's how we calculated it, right? Well, how are we going to calculate our constant multiplier? What's the formula for that, right? We're now dealing with something different than rate of change. We're dealing with constant multiplier. I want to know, how do I calculate it? How do I figure it out? I'm going to give you a formula for that. Your constant multiplier is a ratio, you guys. We are trying to figure out what we're multiplying by to go from one output to the next. Well, how do we figure that out? We take the next output and we divide it by the current output. So we are taking our y2 and we're dividing by our y1. Notice we don't need to involve our input at all for this, okay? We are only working with outputs here. We do not see any x's in this formula. We are only working with y's. We're only working with outputs, okay? We're comparing one output to another. That's how we're going to get our constant multiplier. So I'm going to shrink myself here so you can just sort of see what's going on. So let's take a look at this, okay? Let's take a look at what this means. So let's say we call our current output y1, or y1. Let's make it 4, okay? And then our next output, our y2, is 8, right? After 4 comes 8. If we plug it into this formula, that gives us y2 over y1, which equals 8 divided by 4. And what does that equal, you guys? 8 divided by 4 is 2, which means that our constant multiplier is 2. And all I did to calculate that was I picked 2 outputs and divided them. All right, my second output always goes on top, and my first output always goes on the bottom. And that will give me my constant multiplier. There it is, right? We knew it should be 2, and that is indeed what it was. Okay, so now we have a formula to calculate our constant multiplier, which is great. That's super exciting. It's just like when we were doing linear functions and we had a formula to calculate our slope, our rate of change. Well, now we're doing exponential functions and we have a formula to calculate our constant multiplier. Beautiful. So again, when we think about comparing linear functions and exponential functions, we had our slope, our rate of change with linear functions, and now we've learned we have our constant multiplier for exponential functions. Well, we also had another really important piece of information with linear functions, which was our y-intercept, and we call that our initial value. As it turns out, you guys, that's just as important for exponential functions. We should be wondering, what would the initial value be for this situation, right? We had an initial value with linear functions. Let's see what our initial value would be with exponential functions. How do we figure that out, okay? Stop and think about it for just a second. I want you guys to take a moment to stop and think about what you think the initial value for these bacteria cells was for this situation. Just take a minute and think about it. Okay, so with this situation, 0 days having gone by, that's where this all started, right? How many cells did we have, you guys? We had 1. We started with 1 bacteria cell, right? No time has gone by. Just like with our linear functions, we're thinking about when no time has gone by, right? That's our initial value. Well, when no time has gone by with our bacteria cells, we have just the 1 cell that we started with. They haven't started splitting yet. Okay, before they start splitting, before time starts going by, we just have the 1 bacteria cell. So our initial value is indeed 1 cell. On day 0, when 0 days have gone by, I should say, there was just 1 cell. So for this exponential function, our initial value is 1. So now we have our initial value and our constant multiplier. And we're going to see how we take those two things and put them together to make and define our exponential function. Woohoo! Okay, you guys, let's get back to that letter C. It said, after examining the pattern of this function, can you figure out how to write an equation for it? So we have a constant multiplier of 2, an initial value of 1. Guess what it's time to do? Stop and think. I want you to take a few minutes, maybe 5, to just really stop and think about what these two things mean and how they work together. Use your table of values if you need to. Think about what's happening to go from one output to the next, and how can we write an equation to define it. All right, take 5 minutes to play around. Can you come up with an equation? So I want you to hit pause on this video, and I truly would like you to try to come up with an equation, knowing that you have an initial value of 1 and a constant multiplier of 2. Think about how these numbers play into the values on your table and see if you can figure it out. It is so important that you guys take the time to try to do this without just going to the next slide, all right? I really want you to stop and think about it. I know you can do it. Play around with it. I'll see you in 5. Okay, guys. It is my sincere hope that you did indeed take 5 minutes to stop and think about how the constant multiplier and initial value, how we can put them together to make a beautiful equation. And this is like the coolest part, you guys. This is the part where we get to take everything that we've just learned and talked about and put it together in a beautiful way. This is exciting stuff. I'm just going to take a minute here and just stop because I want to stress the importance of you stopping and thinking when I ask you to on these online lectures. We are not in class anymore, you guys, but we can still do this. However, you need to make sure you are investing yourself into these lectures by participating in them. It's just what I talked about in that tips and tricks video. You cannot be a passive learner when we do these online lectures. We are not in class, and you do not have your group to sit there and talk to anymore and bounce ideas off of. So it is imperative that when I say take 5 minutes to stop and think, you actually take 5 minutes to stop and think about it. That is where you are going to come up with ideas and form patterns and start to see what's actually happening. That's where you're going to come up with questions and insights, exciting stuff. But you can't do that if you don't take the time to stop and think. And it is just so much more important now that you really do that, because it can be really easy to just say, I'm just going to watch the next slide because I know she's going to give me the answer. Don't do that. No. Stop and think. Come up with ideas. Come up with insights. That is going to make the difference between doing well in this class online and not doing well in this class online. Take the time to stop and think. So if you did not take 5 minutes to stop and think on the last slide, do it now. Okay? So do it. Click pause. Take 5 minutes to stop and think. All right. So now I am going to assume you have all taken the time to click pause on this video to stop and think about what's happening. So I always say it, you guys, your independent and dependent variables are just so important. They're like the key to unlocking so many of these problems, okay? So much depends upon them. So always go back to them, always put them back into context each time you're answering a new question, and especially when you're forming your equations. So let's just quickly get that back into our brain. We labeled D, the number of days gone by. That was our independent variable, our input, okay? And our output, our dependent variable, was what we called C of D, which was just the number of cells after that many days have gone by, right? Super important stuff. So we know that time is going by, so many days are going by, D, and we are getting so many cells after that many days, right? Each day, those cells are doubling, our constant multiplier of 2, and we're starting with 1 cell. That's all the information we want to get fresh into our brain when we come up with this equation. So let's look at it. This is so exciting. Let's look at it all and see if we can find a pattern to generalize into an equation. Okay, so let's look at this. Let me talk about this stuff I just threw up on there. So C is our number of cells. So we want to figure out how many cells do we have after 0 days have gone by, right? That's all this is saying, the number of cells after 0 days. And we already know that's 1, right? We're starting with 1 cell. That 0, it means that no days have gone by. 0 days have gone by. Remember, D is number of days gone by. So 0 days have gone by, which is why there's a 0 there, okay? So no time has passed. It's just like when we did linear functions and no time had passed. That was our initial value, right? No time has passed. These cells have not started doubling yet. How many did we start with, you guys? We started with 1, right? Okay, well, let's look at how that relates to our initial value and our constant multiplier. How can we get 1 using those two things? Well, as it turns out, if we take our initial value and multiply it by our constant multiplier of 2, right? Here's our initial value. Here's our constant multiplier. Well, if we raise our constant multiplier to the number of days that have gone by, and in this case it's 0, that does indeed give us 1. Any number to the 0 power is 1. So this just is 1 times 2 to the 0, which is 1, and that gives us 1. That's what we wanted, right? We wanted 1 cell after 0 days have gone by. Okay, let's think about it some more. It probably feels a little funny, what I just said, because we need to extend this pattern and we need to continue to see if it works, right? So let's just keep going, all right? It's okay if you feel confused right now. bear with me, trust me. Let's look at another one. Okay, so now let's look at 1 day having gone by, right? So we want to know the number of cells after 1 day, okay, I'm plugging in 1 for D, has gone by, all right? Well, as it turns out, we know we are just going to take that first cell that we had and double it, right? That first cell we had is going to split. We know that means we're multiplying by 2. That's our constant multiplier. So we're taking that first cell and multiplying it by 2, which gives us 2 cells. Does that work out with the pattern we discussed above? Let's see. Can we get 2 if we apply that pattern? So we said it was our initial value multiplied by our constant multiplier raised to the number of days gone by. So here, 1 day has gone by, right? Anything to the first power is just simply itself. So this is 1 times 2 to the first power, which is simply 2. What does that give us, you guys? It gives us 2. So yes, it did work again. Well, let's see if this pattern holds true. We are mathematicians. We know we need to test this out more than 2 times. Let's try it again. Let's look at the third day, or excuse me, the second day. All right? So now 2 days have gone by. I want to know the number of cells after 2 days, D equals 2, have gone by. So we took our first, so let's go back to day 1. We had our 1 cell on day 1, and it doubled. That gave us 2 cells, okay? Excuse me, we had our 1 cell on day 0, and we doubled it to give us 2 cells on day 1, right? Then we have those 2, now we have those 2 cells. What's going to happen to those 2 cells, you guys? They're going to split. They're each going to double, okay? So we need to double those 2 cells to give us 4 cells. Let's see if that works with our pattern again. So we said we were starting to notice this pattern of our initial value being multiplied by our constant multiplier raised to the number of days that have gone by. So here we have 2 days gone by, right? Our D equals to 2. Well, let's see if this works. 1 times, what's 2 squared? 4. Huh. It did indeed give us the 4 cells we were looking for. Interesting. All right, let's extend it one more time. Because you guys, as a mathematician, I'm just not satisfied enough yet. I just need to make sure this pattern holds true. So now let's look at 3 days having gone by. All right, let's check that out. So we know on day 0, 0 days having gone by, we had 1 cell. After 1 day has gone by, we have 2 cells. After 2 days have gone by, we now have 4 cells. Let's look at 3 days having gone by. So I want to know the number of cells after 3 days. My D equals 3 here. Okay, I started with 1 cell. It doubled to give me 2 after 1 day. Then it doubled again to give me 4 on the second day. Now I need to double it again for the third day. So I have 4 times 2, which equals 8. Okay, so I know that I have 8 cells after 3 days, okay? Let's see if our pattern held true. Our initial value times our constant multiplier to the third power. Why the third power? Because we're on day 3, right? Okay, does that equal 8? Let's find out. 1 times 2 to the third, which is 2 times 2 times 2. You can think of an exponent as copies, a copy maker, right? If I have 2 to the third, I have 3 copies of 2 being multiplied together. So 2 times 2 is 4. 4 times 2 is 8. Huh! It worked. Okay, and it is indeed true. This does hold true for our entire exponential function here. So if we were to generalize it, we could say that the number of cells after D days is equal to, we're starting with 1 cell and we're just continuing to let it double. Every day it's doubling. So I'm multiplying by 2, 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 right? So generalized, we have our initial value multiplied by our constant multiplier, which is being raised to the power of the number of days gone by. Okay, that's how we would generalize this equation. Take a second, let it sink in. Just look at what we have right here, okay? And think for I'm not going to say half a second, think for like 5 minutes about where each of these numbers came from. Where did the 1 come from? Where did the 2 come from? What's this D mean? Think about it. Hit pause. It will make all the difference. And then we'll talk about it in a second. Okay, so my hope is that you pause this, you thought about it for 5 minutes. This equation is hopefully starting to make more sense to you, okay? Our equation here would be the number of cells after D days is equal to our initial value of 1 cell multiplied by our constant multiplier of 2, right? Raised to the amount of days gone by, okay? So this just means that we are constantly doubling. Every day we're doubling. And the number of times we double just depends on the amount of days gone by, which is why this is being raised to the D power. But we can't forget that we started with 1 cell. That's going to, if we had started with a different number of cells, we would be getting a different answer. So that initial value is very important, you guys, okay? And this is how we write our exponential equations. So we have our initial values here, right? Always our initial value, and our constant multiplier here, okay? Woohoo! We put it all together. Very good. Let's give ourselves a round of applause. Okay, so my round of applause didn't work on the last slide for some reason, and I think we all deserve a round of applause for working our way through building that exponential equation. So I'm going to give it to us right now. Okay, so now let's actually talk about what is an exponential equation, right? We just built our exponential equation for our function about bacteria. Let's talk about what exponential equations are in general, okay? So an exponential function is defined by an equation of the form. Y and f of x are really sort of the same thing. We use f of x when we're talking about a function. So f of x is equal to a times b to the x, where a cannot equal 0 and b cannot equal 1 and must be greater than 0, okay? So let's sort of break this down a little bit, okay? X is our independent variable. So for us, right, our little x up here, that's our input, our independent variable. For us, that was the number of days that have gone by, okay? That's where the exponent comes in. Notice that your independent variable here is being raised as a power. When we had our linear function, it was not being raised as a power. It was being multiplied by our constant rate of change. Here, we're taking our constant multiplier and we're raising it to that power. Okay, that's important, you guys. All right, so we have x as our independent variable, our input. Here, for us, it was our number of days gone by since this bacteria started splitting. Okay, there it is. Y is our dependent variable, or f of x, just another name for it, or our output. Okay, that should make a lot of sense. It was the same when we were dealing with linear functions. Okay, our output is what we're looking for here. So that's what our equation is being set equal to. A is a constant called the initial value. So this is what we sort of stumbled upon the last few slides, right? Here we have A, our initial value. It's just what are we starting with? In our situation, we started with 1 cell. And then it started splitting from there. We didn't start with 2 cells or 3 cells or 4 cells. We started measuring time from when we had 1 cell. So our initial value here was 1 cell. Notice it cannot be equal to 0, okay? And why do you think that is? Take a second to think about it. If A was 0, what would happen to everything else, you guys? right? It would zero out the whole thing. If we multiply by 0, we're going to zero out everything, all right? Just fun little things to notice as we go. B is a constant. Again, constant meaning it doesn't change, right? A and B are constants. They're not going to change. They'll always be the same in our equation, okay? And it's called the constant multiplier. So we learned that with exponential equations, we're not looking at a slope, a rate of change. We're looking at a constant multiplier, right? We're not adding and subtracting here. We're multiplying. So we're looking at our constant multiplier, and that will stay the same the whole time. It's constant. And notice it has to be greater than 0, okay? And it cannot be equal to 1, right? Think about why that is. Why shouldn't it be equal to 1? Just think about it for a second. Look what's happening here. If we put a 1 here, oh my goodness, that's a terrible one. Let me write it again. So if we put a 1 here, right, for our B, we're raising 1 to any power, you guys. It's going to equal 1, right? So that would just make our equation equal to A the whole time. And then we would actually have a line. So it can't be 1, because 1 to the first power is 1. 1 to the second power is 1. 1 to the third power is 1, right? 1 times 1 times 1 is 1. That would make this whole part of the equation equal to 1, which means we're just multiplying our initial value by 1. We're back to a line, okay? So we know that our constant multiplier has to be greater than 0. It's not going to be negative, okay? And, but it can still be a decimal. It can be a decimal. And it cannot be equal to 1. All right, so these are the different components of our exponential equation. This is how we define an exponential equation. It can be written in this form. So yay! Now we've made it to part E, our last question for this lunch. Woohoo! It says, use the equation to find out how many cells there would be after 30 days and how close was your estimate. So if you remember way back when we first started this lecture, I asked you to come up with some sort of an estimate for just a brave guess for how many cells you thought there would be after 30 days. And now we can actually figure that out. We have an equation that we have come up with that we can figure out, right? The number of cells after D days is equal to our initial value. We started with 1 cell, multiplied by our constant multiplier raised to the power of how many days have gone by, okay? So what we need to do is plug in 30 for D, right? So I would like you guys, we want to know after 30 days, see if you can figure it out. So stop and think and see if you can figure out how many cells of our bacteria are we going to have after 30 days time. Okay, and compare it to your estimate. So take a minute and do that. I just want you to actually do it. So I'm just going to sit here for a minute because I want to make sure you're doing it. Whip out your calculator, plug it into the equation, right? Should all be doing this. 1 times 2 to the 30. And we'll talk about our calculators in a minute. Plug it in. See what you get. So hopefully you've done that. Okay, so how would you plug that in, you guys? You're going to take your graphing calculator. 1 times 2. Use this little caret thing right here to raise to an exponent. So I'm going to hit that caret, and then I'm going to write 30. Hopefully. Okay, 1 times 2 to the 30. Press enter. There's my answer. It's enormous, right? Guys, exponential growth is crazy. It's crazy. Okay, so after 30 days means D equals 30. Plug D into our equation to get, woohoo, holy guacamole. This is a lot of cells. Okay, this is more than 1 billion cells, you guys. A lot of cells. So, let me make myself go smaller. Don't forget your units. So important. So many of us lose points here Do not forget your units. It is imperative. It's incredibly important, you guys. This is an important piece of information. What did we just figure out? We didn't figure out the number of days gone by. That would be an incredibly ridiculous amount of days to have gone by. We figured out the number of cells. And isn't that wild? I mean, just look at how these cells grew in a month's time. Exponential growth is nutty. Over 1 billion cells, you guys. Crazy, crazy, crazy stuff, right? So really take a second to stop here and just make sure your answer makes sense, okay? There's my surprised face. Over 1 billion cells. Okay, so I'm going to come back on. Here we are. All right, so I wanted to just take a quick moment to just show you a graph of this equation, okay? I put it into a little generator I found online. This is what our graph of our exponential function that we generated looks like. So this is a graph of how the cells are growing, how many cells we have after d days, right? So I literally plugged in 1 times 2 to the d, and this is the graph that got generated. I want you to notice, guys, as day, remember our days are down here. This is our days. That was our input. And this is our number of cells. That's our output. Guys, look at this. Look at how quickly this increases. It's insane, right? So after only 4 days, look how much the number of cells have jumped. Exponential growth is crazy. Notice how quickly the output increases, you guys. Look at that. I don't know if you've ever heard the phrase, this is growing exponentially. That implies that we are having this really big increase of output over smaller bits of input, okay? I mean, our input is only increasing here a day at a time, but look at how quickly the number of bacteria cells spikes up like that. It's crazy, right? It's just something good for us to take notice of, okay? All right, so let's sum up what we've learned, all right? Sum up 3.1 here. We learned that exponential functions have inputs that increase by a constant while the outputs change by a constant multiplier. This was different than our linear functions. For our linear functions, we had our inputs increasing by a constant while our outputs increase or decrease by a constant, okay? Now we're dealing with constant multipliers. We're not adding and subtracting our outputs anymore. We're multiplying. Exponential equations are written in the form of this, right? F of x equals a times b to the x, where x is the independent variable, our input. That's the part being raised to the exponent, you guys. Super important to take note of that. Y is the dependent variable, the output. A is our constant, the initial value, how much we're starting out with. And B is our constant, called the constant multiplier. Okay? So please feel free to email me with any questions. You can go back to that PDF document that I sent you with this link and check out your homework so that you can practice all this really great stuff. And I will see you guys online again very soon. Thanks for tuning in. Remember to do your homework, guys. It's so important to practice. It's going to be that much more important for you guys to make sure you get your homework in and practice, 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 practice while we're online, okay? I know you can do it. Bye.